everybody. Thank you for joining. This has been about a year in the work of just hard labor intensity between all of us. So I myself, I'm Heather Rose. I'm the TEM product manager for Hitachi here in America.
Hi, I'm Pushkaraj Deshnuk. We make specimen orders for cryo specimens.
My name is Adam Manganello. I'm Director of Sales and Marketing for AMT. And so we specialize in TEM imaging systems and a whole array of products.
And today we're doing a live cryo screening demo. And as you might feel in the room today, it is a bit warm. Anyone else a bit warm, or is that just me? It's just me? All right, because I'm a little sweaty. Sorry. And then also the humidity, being in Cleveland, Ohio, of course, isn't the best. But the good news is that we were able to successfully transfer a real cryo sample that was shipped in from New York Structural Biology. I want to say thank you to all the national labs across the country. They're really the heroes here to help me do exactly what I did here today. And I really appreciate all their help and their effort in doing this with me. So we're screening a sample currently as we're talking, just kind of doing a little background introduction. As I mentioned, my name's Heather Rose. My background's in material science engineering, and I joined Hitachi about 3 years ago, and now I'm at their facility in Hillsborough.
My name is Adam Manganello. I'm a biologist by trade. Sort of cut my teeth in physics and optics, and that's how I found my way to AMT. So I'm more specialized in sort of optical coupling and how we design camera systems. I got my undergraduate degree in Massachusetts, and I've been here since 2015. And Pushkar?
Hi, Pushkar. I am the founder of Simple Origin. We make cryo specimen holders for the application you're about to see. Okay, so what we're going to do here is half an hour ago, we did a cryo transfer, like Heather mentioned, from the specimen we got from New York Structural Biology. So we have already finished that. What I'm going to do is repeat the process so you get an idea of what we have done. So what you see is the cryo transfer holder. I'm going to go into the basics, assuming there are some audiences who have not done cryo transfer. Forgive me if it's too basic. So we have a cryo transfer holder here. The components is the specimen holder that you see on the TEM right now. And then we have a workstation. So the workstation is designed so that you can get a cryo specimen and load it to the holder without contaminating it. And we have a temperature monitor that actually shows you the temperature of the holder at the tip. So what you want to do first is make sure you have a specimen that is in liquid nitrogen, frozen, biological specimen. And before you start the process, what we have here is a knob that you can slide the specimen stick out. We have a specimen tool, and the idea of the specimen tool is it's very lightweight and low profile, so you don't transfer heat energy from the tool itself to the holder when you're doing a cryo sample transfer. There's a slot in there that you put the tool in, and you gently rotate it. Lifts up the specimen clamp, and you see it. You leave the specimen clamp open before you start cooling, so you don't have to fidget with it when everything is cold. Then you take your liquid nitrogen and start cooling the specimen holder. And at the same time, you want to make sure you cool the specimen tip and the workstation. Try to keep it closed as much as possible so you don't contaminate it with humidity from the atmosphere or from you breathing into it. To monitor the temperature of the tip You have to cool it till it reaches to liquid nitrogen temperature below minus 190. And that's when you start working with it. You want to give it. So for those who don't know, the temperature rises above minus 145, minus 150, you're going to get devitrification of the ice, and basically your sample is going to be. While it's cooling, actually, you would normally wait till it's minus 190 or below. But just to save time, I'm going to just continue with the process. You're going to get your cryo sample, and this is going to be liquid nitrogen. You're going to bring it and keep it in the workstation. You want to make sure you maintain the level of liquid nitrogen so your samples are not destroyed. I would also like to mention that please make sure that the holder that is pumped overnight before you start using, so you can actually maintain a low temperature, and also it's very stable when you're imaging in the TEM. So once everything is below 195 or 194, you can open up your grid box. Oh, before you do that, make sure you cool your specimen. Open up your grid box. This is a small heater that you can that helps you keep everything clean. You can use your tweezers again, cool it, liquid nitrogen. You can use it to pick up your specimen. You can load it. Once you have loaded your specimen, it's a one-step simple process where you can pull your this clamping tool, and you can flip the lid and press it down on it. So now your specimen is clamped. So the clamp is designed such that there is a constant spring force on the specimen which maintains the good contact with the cold tips. Technically, you'll be doing this at minus 190. So once you do the transfer, you need to actually pull the tip into the holder. And the next step would be getting there, but I'll stop this. And the next step would be you take your workstation. You take it next to the TEM. At this point, you'll remove it and put it in the TEM.
Thank you, Pushkraj, for the great transfer. So as you noticed, we did this a little earlier today. We transferred the sample about a half an hour before our show started. And if some of you do not know about the HT7800 that we brought here today, this is not a field admission TEM. This is a thermionic TEM. So this means that we can put in a Lab 6 or a tungsten filament. So we can go from anywhere from 20 volts or 20 kilovolts to 120 kilovolts. So today we're operating at 100 kV. So this is not 200, this is not 300 kV. This is a Lab 6 system at 100 kilovolts. And if some of you are unfamiliar, we are running SerialEM, which is a free software that you can download at any time. So it's compatible with our system. But before I even put in the sample, we cooled down the TEM using one of our latest products. So I'm going to take you over to the TEM, and you can see this arm sticking out here. This is our retractable cold finger that we just released, and we have a cold trap in the back. And the system takes about 10 minutes to cool down. So you can see these vacuum levels here in order to achieve an ideal vacuum condition to have a cryo sample without it freezing over or having any sort of contaminants. So if from the illustration here, this is the retractable cold finger and the trap is in the back. And then these dewars last about 9 hours without filling it at all. I mean, you could continuously fill it if you wanted it to last longer, but about 9.5 hours for these dewars to last. And so looking further into the retractable cold finger here, again, this is attached on the side of the column, and this is something that is retrofittable. So on current TEM models that are in the field, this is something that could be added later. But talking about how this is physically possible. So we have these blades that come in. above and below the sample to keep the area nice and cold, prevent it from any contaminations. So you can see this fits right in between the pole piece of the upper and lower objective lens here. And so this is where our sample will sit in between these blades to make cryo observation physically possible. Now, the benefit of having these blades is versatility. So we don't want to make a dedicated cryoscope. We're not aiming to make a dedicated cryoscope. We want to improve the versatility and give you the applications ranging from doing cryo, or if you wanted to do EDS or STEM or tomography. This is just an additional application for this tool that when you are ready to do cryo screening, you insert the blades using the wheel, allowing you to do cryo observation. And then when you don't want to do cryo observation anymore, they can be retracted. And so looking at the temperature and vacuum time, as I mentioned on my previous slide here, we're looking at around 9.5 hours that the system can last for, and the temperature of about -176 Celsius. So it keeps the sample nice and cold, preventing any sort of contamination. And so if we're looking over here, you can now see that I have a sample under ice. This is virus particles or virus-like particles that are being screened using SerialEM. So it is frozen, and just if anyone forgot where we are, we're on a show floor. I'm not in a laboratory, and so just showing the versatility of this system. I've been running demos all day for various customers. I've been looking at anything from polymers to thin sections to asbestos, you name it. I've been doing it all. I've been doing tomography, montaging, and now getting ready for the demo. Now I'm doing cryo screening. So just adding to the versatility of the scope to further improve laboratories across the country, especially places like core facilities or universities in general, to help add to their capabilities. So I wanted to further look at the vacuum data on the system. So of course, right now I'm only screening one grid, but throughput is one of the most important things when it comes to cryo screening. And I think any lab that does cryo knows that throughput's very important. So what I've done in this experiment is I have removed the simple origin holder, I put it in the transfer holder, and then I put it back in the scope and over and over and over again to see what our vacuum levels can hold and how many times I can repeat this process. And after about 5 times, I got tired and said, okay, five's pretty good, but I kept going because you can see around the range that it's fairly stable in terms of vacuum levels. So before the vacuum or before the holder was inserted, we're looking at these values, and then afterwards, the recovery is very quick. About 10 minutes after the holder was inserted in the tool, we're looking about 10-ish minutes until that full recovery. And then pulling it back out, again, we're looking at less than 10 minutes of that vacuum recovering very quickly, and just over and over and over again. I don't have to go through every value, but just to show how close the range is and how stable the system is as I'm pulling it out and putting it back in, that the values are all very similar to each other. So again, adding to the throughput and helping our system do more samples. So going through here. So you can see that the values are all very similar to one another, helping the system with the throughput. So unfortunately, we won't have time to go through CryoSpark, which is a reconstruction software for cryo samples. But I have previous data that actually, if you want to see, I have a poster at number 273 using apoferritin data. So these images are of apoferritin about 3 hours after the holder was inserted. And then these images are, well, it says 3, but these are 9 hours after the holder was inserted. And you can see that the ice is virtually unchanged after 3 to 9 hours. Again, I don't have 9 hours to show everybody here, but But then I took it a step further and I put these micrographs that I took from this apoferritin run into CryoSpark. I performed a template picking. I trained that template to then produce 2D classifications. So you can see here my apoferritin reconstruction, or my 2D classifications of apoferritin. Here's a resolution of 12 angstroms, and then at the bottom here is a 6 angstrom resolution. So I think from here, Adam is going to take over and talk about how these micrographs were formed.
Perfect. So thanks, everyone. So I see a lot of familiar faces here and a lot of unfamiliar faces. So I'd like to just thank you all for coming out. And as Heather said, I'd like to take a little chance just to talk about the imaging technology that's used to take these grayscale images here on the TEM. So on this system here today, we have one of our NanoSprint 15 Mark II cameras. And to you, that probably doesn't mean anything. Behind that, we're using the latest, cutting edge scientific CMOS technology to generate the images. And so I talk a little bit about how our company adapts sensors like that because they're rapidly evolving in the market, and how we build the optics and pipeline to deliver that data, and why we think it's important. So as I said earlier, I'm from AMT Imaging. We've been around for a long time. Our company started in Massachusetts in the early 90s, where I think we're credited with pioneering 35 millimeter port digital camera imaging. So generally that was a film plane. And we came out with the first sort of 1 megapixel cameras. Comparing the technology from then until today, things are now 61 megapixels for pathology, and the camera system that we have here tonight is a 15 megapixel. We've been delivering for 30 plus years. We currently serve 2,500 customers worldwide. Our market base is installed in the United States, with our second major market being Japan and China. We're also globally represented. So most of my job is dealing with our distribution network worldwide. We obviously service direct here in the United States. In Europe, we have a service hub out of Vienna in Austria. We also have one out of Shanghai in China, with distributors in every major region. So different customers want different things. So the theme here tonight is cryo. In the overall market, sometimes people want to favor field of view. So the goal here is sort of sensitivity, but I did want to just sort of state that we make cameras for every port on a conventional TEM. So if you do low mag work, we probably have a solution for you. And that all starts with light generation. So one of the things that we do special at AMT is we make our phosphoscintillators in-house. And so it turns out that that's very much an intersection of art and science. And so I don't know if any of you have ever spun coat things or deposited powders and resins. It's not exactly a thing that works well, and so we have to do it a lot. But in doing that, we've developed an expertise in making things really high resolution and uniform. And so there's a handful of suppliers in the world that do this type of stuff. But when pixel densities on the sensor side went down, below 7 microns to 6, and now you're 3 and 2.8, there's an intersection of data transfer where if your phosphoscintillator is really thick, and I'll show that here in the next slide, you get blurring. And so the next sort of piece of this, I'll segue into lenses, is that, we do our best to make as much light as we can at the source of this optical system, and then try and preserve it as much as we can going through down to the sensor. And so this is kind of a real example of what that looks like on a 200 kV machine. So the thickness of the phosphor very much translates into the sharpness of the image quality that you see. And the systems come apart in a modular way. So these are just examples of some of our smaller lenses here. That's not what we have here tonight. What we have here tonight is a Mark II lens, which is a large multi-element finite conjugate lens with a really narrow back focal plane. So what that means is, when we go to the market and we buy sensors, surface flatness is very important. That's one of the things that our competitors sort of struggle with is, large sensors can come out, but you may only be able to sample 4 megapixels or 8 megapixels of that in a uniform manner. And then you get sort of lost in terms of what is available to sample. And so with the lens, if we make precision optics, we get a large field. In this case, it's an 80 millimeter field that we're sampling. And then we transfer that down to about a 65 millimeter active area on the sensor. Also by doing that, one of the major examples that I talked about right at the beginning is that sensor technology is rapidly evolving. So right now, and at the end of this talk, I'll talk about sort of the next generations of things that are coming out. By building lenses the way we do, we're able to rapidly adapt. So the NanoSprint 15 Mark II system that we have here will pretty easily be changed out to the next generation without having to do a major optical design because we overshoot a bit. It turns out it's really hard to buy high performance commercial lenses. So when you go to the market, if you go to a company like Zeiss or Rodenstock, or there's a few vendors that makes things for commercial videography and sort of telecasting, those tend to have MTF ranges of around 40%, oftentimes it's 30%. Our Mark II lens that we have here tonight is 75% at a sampling frequency of 120 line pairs per millimeter. I feel like I'm probably speaking another language, so I figured I'd give you a real example of what that looks like. And so when we test these lenses, we make them and they come into our office. We look at an Air Force test pattern, which is a substrate that has increasing intensity in imaging sampling frequency. And so what happens with an imaging system is, in this case, we have the same sensor, one with a commercial lens and one with an AMT lens. And on the outside, you can see, this information is preserved. But as things get more and more dense, they're lost. And in imaging, like in TEM, that translates into information lost in your final image. And so if it wasn't there to start, you're never going to take a picture of it. So we do everything we can to manufacture lenses with the highest MTF so that the image is of high quality as possible. And so on this roadmap, CMOS sensors were large, fast, and really noisy. And in the late 2000s, we got our first 2K by 2K scientific CMOS sensor. And this is the first sort of system that was fast with low noise. But it wasn't really popular because at the time, things had sort of moved to 4K in the imaging market. And so it wasn't until 2019 when we first got our hands on this 15 megapixel sensor that we adapted for a more wide range sort of format, but still had the low 1.7 electron read noise and high frame rate of 30 frames per second. And then so just a bit of insight on where we see the market going. It's going two ways. They're getting larger. So we just started developing the first 10K by 10K system for connectomics. And then we also see things getting more favoring this sort of low 100 kV single particle cryo screening, where the noise is getting driven down even further. So right now we have 1.7 electron read noise in an image. It's going down to less than 0.5. If you run the camera slower, you can get down to 0.3, which really means your signal to noise in your image acquisition is incredible. So you don't need a lot of beam to take a bright image. And so Heather's system is running now. I think we're probably running with an exposure of like 400 milliseconds, and you have great grayscale. And that's what it translates to in real time. And so I think I talked about it a little bit. This innovation really comes from sensor level innovation, where amplifiers are added to every pixel. Digitization happens instead of bank amplifiers, it's happening on each column. And I just wanted to show a graph of sort of how things are, transitioned in the last 10 years. We went from, about 8 electron read noise to 6, and then we're going down below 2. And then these numbers are going to even, continue to go lower and lower. And then we see advances in QE as silicon technology develops. And as I said in the beginning, I figured I'd take a little bit of time just to talk about the sensor technology because it's how we make the images here tonight. And at AMT, we do a little bit of everything. So connectomics, pathology, material science, and now cryo at 100 kV on a 7800 on the show floor. So I'm going to hand it back to Heather, and thank you for your time.
I just wanted to connect everything together. So let's start from the beginning. We had our transfer holder using our side entry holder. And then we have our system, our TEM, that has new technology, new product to make this all happen, stable vacuum system to do high throughput. And then we additionally have a CMOS camera to allow the image quality. I think everyone has seen that, yes, we're collecting the holes. So I'm gonna go ahead and stop the collection. And so if we saw here, we have our SerialEM software, and kind of going through what I was doing and what I was collecting and why am I looking at these holes, and kind of backing it up just a little bit. Now that we know about all the technology, the camera, the holder, the system, what exactly are we doing here? And so using SerialEM, I'm able to collect this whole view map of my whole grid. And then from my map, I'm able to then zoom in to see which grid square has the best ice quality. And so thankfully, I got very lucky. It's a high risk because a lot of the time you put in a sample and it's completely iced over and you're very sad and you gotta do it all over again. So I got very lucky and I had the luxury of picking the grid squares that I wanted. I had a whole bunch to choose from. So I chose the grid squares and then I looked at them and decided that this grid square looked okay. And then I was able to do like a hole finder and find the holes that have the best ice quality. And then from those holes, I can refine it to then collecting images of the particles within the holes. So we're trying to shoot for the holes with the best ice. That's where the grid will be the thinnest and the ice will be the thinnest so that we can clearly resolve our particles. So for example, we have a whole bunch of holes that I've imaged here of the virus-like particles. And I can then take these micrographs. I've maybe collected about 100 now of these whole micrographs. And then from there, I can import them into the software I was talking about earlier, CryoSpark. CryoSpark is free for academic use. And then I can then have CryoSpark pick out the particles that I want and then turn those into classifications to then help me decide what my shape of my particle looks like. So having a system that can do this cryo screening, especially as a thermionic and not needing a field admission, I can do much more with this tool, get an idea of what my particle looks like, and utilize national labs across the country that have maybe 200 or 300 kilovolts systems. So I don't have to look at field admission systems. I can look at a thermionic for screening and then utilize these national lab facilities to then do the full reconstruction. If you're not familiar with how the national labs work, some of them do require that you have screened your particle so that when they spend their time and resources on the more expensive tools, that they know what your particle looks like beforehand. So it's a prerequisite to get your image as a data collection. So utilizing SerialEM allows me to collect these images automatically without much user intervention. And so I can just let it go and collect all the holes that I need to then do the reconstruction. So then we have this whole package. Again, we have the holder here, the camera, the system, the software to enable us to do more, to allow us to have this easy entry for cryo. So it doesn't have to be this barrier anymore. Cryo doesn't have to be this large, expensive, intimidating application. We can have this as now an application for all labs across the country, whether you're an undergrad, a graduate, or a professional laboratory. You can fit your system and have many users of many experiences do cryo screening now. So I wanted to just finish up and invite Adam back and Push Garage because they've really helped me with this project. And I wanted to say thank you for their help as well. So
You're welcome.
Thanks for joining.